Imagine drifting through the universe so far from home, so far from any star, that darkness becomes your only companion. Out here, between galaxies, the cosmos is quiet, almost peaceful. But even in this seemingly endless stillness, there are places where the universe roars, places where space folds, where time bends, where reality itself falters. And there, in that quiet darkness, something stirs, something waits, something with gravity so strong that even light cannot escape. A cosmic mystery that has haunted human imagination ever since we first dared to look up at the night sky and wonder. A black hole. To understand the power, the terror, and the beauty of a black hole, we must begin long before it exists, when it is nothing more than a star. A star, massive and blazing, born in a collapsing cloud of dust and gas, shining brightly for millions or even billions of years. It fuses hydrogen into helium, helium into heavier elements, building the very atoms that make planets, oceans, life. It is a factory of creation, sculpting the universe with light. But all stars are locked in a constant battle, a tug of war between the outward push of nuclear fusion and the inward pull of gravity. For most of a star's life, these forces balance perfectly, but even stars cannot burn forever. And when a massive star runs out of fuel, its outward pressure fades. Gravity, patient and relentless, finally wins. The core collapses, not gently, not slowly, but catastrophically in a fraction of a second. The outer layers explode outward in a supernova so bright it can outshine entire galaxies. The core, crushed beyond comprehension, collapses into something infinitely dense. A black hole is born. But this is not a simple object. It is not a sphere, or a void, or a hole in space. It is a region, an area where the fabric of space-time has been stretched into a cosmic funnel. A place where gravity becomes so intense that the laws of physics as we know them begin to twist, distort, and eventually break. Yet the most dramatic part of a black hole is not itself, but the boundary surrounding it. The event horizon. A line in space where escape becomes impossible. Not because a physical barrier blocks your way, but because every path, every trajectory, every possible future leads inward. Cross the event horizon, and you are falling forever. But before we cross that boundary, let us explore the space around a black hole, where its influence reaches far beyond what the eye can see. Matter spirals toward it, forming an accretion disk, an enormous storm of superheated gas orbiting the black hole at nearly the speed of light. This disk glows with the intensity of 1,000 suns, heated by friction, magnetism, and gravity itself. The gas streams, twisting and whipping around the black hole in a violent cosmic hurricane. Jets of energy blast outward along the black hole's magnetic poles, traveling thousands of light years into intergalactic space. These jets can be so powerful that they reshape entire galaxies, triggering bursts of star formation or stopping it entirely. Black holes, contrary to their reputation as destroyers, are engines of creation. But let us slow down. Let us imagine we are floating just outside one of these cosmic titans. Imagine the strange distortions around us. Light bending into arcs, stars stretching into ribbons as their photons take curved paths through warped space-time. If we looked at the black hole's edge, we would see something surreal, a glowing ring around perfect darkness. This ring is not the black hole itself, but the last light that manages to orbit it. Photons circle again and again, trapped in a gravitational dance, until finally spiraling inward or escaping into space. This is the photon sphere, a place where light can literally orbit. But what lies inside that glowing ring is something even more profound. The shadow of the black hole, a region so dark, so perfectly empty, that nothing within it can ever return. This shadow is not the black hole's surface, because it has no surface. It is simply the outline of doom, the silhouette of the event horizon. Now imagine drifting closer, slowly, carefully. Time begins to behave strangely. Your heartbeat continues at its normal rhythm. Your breathing feels steady. Your body works as it always has. But the universe around you starts to change. A distant observer, watching your fall, would see you slow down. Your motions would stretch into an agonizing crawl. Your image would redden, fade, dim. You would appear frozen at the edge of the event horizon, never actually crossing it. From their perspective, you vanish. But from your perspective, you fall. There is no pause, no freeze, no halt. The moment you cross the event horizon, nothing remarkable happens. No flash, no wall, no sudden shock. But the laws of the universe subtly rearrange themselves. Every direction now points inward. Every possible movement, no matter how you try to steer or resist, leads toward the singularity. It is not a place you fall into. It is a place that pulls the entire universe toward itself. As you continue your descent, gravity stretches you, first gently, then brutally. The pull on your feet becomes stronger than the pull on your head. Your body elongates, atom by atom, molecule by molecule, until you are a thin line of particles moving deeper into darkness. This is spaghettification. But long before you reach the singularity, something else happens. Something more mysterious, something theoretical, something that physicists debate with passion and curiosity. Information. According to the rules of quantum mechanics, information about particles, about energy, about states of matter, can never be destroyed. But black holes seem to destroy everything they consume. This contradiction sparked one of the greatest puzzles in modern physics. The black hole information paradox. Does the information vanish? Does it remain encoded on the surface of the event horizon? Does it leak out slowly as the black hole evaporates through Hawking radiation? Or does it tunnel into another universe entirely? The truth remains unknown. We continue to fall, deeper, darker, toward the singularity, the heart of the black hole, where density becomes infinite and the laws of physics break down. Not metaphorically, not poetically, literally. Equations cease to function. Time and space lose meaning. The singularity may be a point, it may be a ring, it may not exist in the way we imagine at all. Some theories suggest it is a gateway, a doorway, a bridge to somewhere else, a wormhole. The idea is tantalizing. Fall into a black hole and emerge in a completely different region of space-time. Another galaxy, another epoch, another universe. A cosmic shortcut across the infinite. Perhaps black holes are not endings but beginnings, gateways to places we cannot see, cannot visit, cannot comprehend. But even if wormholes exist, they would be unstable, violent, unpredictable. A human traveler would likely be ripped apart long before emerging into a new reality. But the mathematics leaves the door open. Nature may harbor pathways beyond our imagination. Yet black holes don't just shape theoretical physics, they shape the universe itself. At the centers of galaxies, supermassive black holes, millions or billions of times the mass of our Sun, anchor cosmic structures. They influence galaxy formation. They regulate star birth. They power quasars, bright beacons visible across the universe, shining with more energy than trillions of stars. These black holes are not passive observers. They are active participants in the cosmic drama. Imagine a black hole billions of years ago in the early universe, devouring gas clouds and stars, generating jets so powerful that they mold the surrounding galaxy. Without these titanic forces, galaxies might not settle into the familiar shapes we see today. Spiral arms might never form. Star clusters might never coalesce. Planets and life might never appear. Black holes may have helped write the script for the universe. And then there are the collisions. Two black holes spiraling into each other, dancing a deadly waltz as gravitational waves ripple outward. These waves stretch and squeeze space itself, traveling across the cosmos until they reach Earth, where incredibly sensitive detectors pick up their whisper, an echo of a collision that happened billions of years ago. For the first time in human history, we can hear the universe. And what we hear is the sound of space tearing, of gravity collapsing, of black holes merging into something even more massive. Yet even more mysterious are the supermassive black holes. How do they form? How do they grow so quickly? How did a universe only 100 million years old already contain black holes millions of times the sun's mass? No one knows. Perhaps they formed from collapsing clusters of stars. Perhaps they were born from the earliest, most massive stars in the universe. Or perhaps, if some theories are correct, they form not long after the Big Bang itself, from fluctuations in the fabric of space-time. If so, black holes may be older than galaxies, older than stars, older than light. They may be as ancient as the universe itself. But as eternal as they seem, black holes are not immortal. Stephen Hawking proposed that they emit radiation, Hawking radiation, causing them to gradually lose mass. Slowly, extremely slowly. A black hole with the mass of our Sun would take 10⁻⁶7 years to evaporate, longer than the lifespan of all stars, longer than the age of the universe, longer than everything we know. But eventually, they fade. Not with an explosion, not with a collapse, but with a whisper of radiation until nothing remains. The universe, in its far future, long after stars have died, galaxies have faded, and the cosmos has grown cold, will be filled with dwindling black holes waiting out eternity. And in that dark, silent future, the last light that ever shines may be the final flicker of the last evaporating black hole. Imagine that, the universe ending not with a bang, but with a quiet sigh of fading radiation. But until that distant future, black holes remain among the most fascinating, awe-inspiring objects in existence. And yet, the greatest truth about black holes may be this: they force us to confront the limits of human understanding. They challenge our assumptions about space, time, matter, and reality. They show us that the universe is stranger, deeper, and more mysterious than our minds can fully grasp. They push the boundaries of science, philosophy, and imagination. A black hole is not merely a cosmic object. It is a question, a paradox, a doorway, a challenge, a whisper from the universe saying, "There is more." And perhaps that is why we are so drawn to them. Because black holes are the ultimate reminder that discovery never ends, that curiosity is infinite, that knowledge is always incomplete, that even in the vast darkness of space, there are wonders waiting to be understood. We gaze into the abyss of a black hole, not because we expect answers, but because the abyss invites us to ask better questions. And so our journey continues, across galaxies, across time, across the limits of understanding, chasing the mysteries hidden in the darkest places. Black holes may consume light, but they ignite wonder. They may swallow stars, but they spark imagination. They may distort space, but they reveal truth. And in the end, perhaps the true power of a black hole is not its gravity, but its ability to pull our minds toward the unknown, to bend our curiosity, to reshape our understanding, and to remind us that in a universe so vast, the greatest mysteries are still waiting in the dark. Because even as we stand in awe of black holes, we must remember something fundamental. Black holes are not rare. They are everywhere. They are woven into the structure of the cosmos like silent threads holding galaxies together. In the Milky Way alone, there may be hundreds of millions of them, wandering the galaxy like invisible shadows, quiet travelers that drift through the darkness. Some are remnants of stars long dead. Others lie hidden between spiral arms, unseen but detectable by the way they tug gently at the stars around them. And then, at the core of the galaxy, sits a giant, Sagittarius A, a supermassive black hole around 4 million times the mass of our Sun. For decades, astronomers wondered how we could prove its existence. And then, in 2022, the impossible happened. An image. A real image of the black hole at the center of our own galaxy. A blurry ring. A dark center. A glimpse into the abyss. A confirmation that our theories, our equations, our predictions were correct. But we must not be fooled by that soft, glowing ring. Sagittarius A is calm now, relatively speaking. But in the distant past, it was violent. It consumed entire stars, tore apart gas clouds, and blasted jets of radiation far into space. Our galaxy has a quiet heart today, but it was not always so. And as we understand the life cycles of black holes, we begin to understand something else. They are not just destroyers or creators, they are stages in the evolution of the cosmos. They are born, they grow, they change, they evaporate, they die. Imagine billions of years from now. The universe has expanded so much that galaxies are separated by unimaginable distances. Stars are fewer. Light is scarce. The cosmos grows colder, quieter, emptier. And yet, throughout this fading universe, black holes remain, still devouring, still warping space-time, still holding on. But even their reign must eventually end. Through Hawking radiation, they lose mass. Slowly at first, then faster. Until one day, in a universe where all else has dimmed, a black hole evaporates completely in a final burst of energy. A last flash in a universe otherwise silent. And after that? We don't know. Perhaps the universe collapses. Perhaps it expands into eternity. Perhaps new physics governs that distant future. But as long as black holes exist, they remain cosmic landmarks, points where the known meets the unknown, where science meets mystery. Yet even within the mysteries of black holes, there are deeper questions, subtle puzzles that challenge the brightest minds on Earth. One of the greatest involves the horizon itself. We think of the event horizon as a point of no return, a silent border. But recent theories suggest it may be far stranger. Some physicists propose that the horizon may not be a smooth boundary at all. It might be a firewall, a region of intense energy where the laws of quantum mechanics rebel against Einstein's equations. If true, the event horizon is not a gentle boundary, but a cosmic incinerator. But if the horizon is smooth, as Einstein predicted, then the paradox deepens. How can the universe protect both the rules of relativity and the principles of quantum mechanics? Theories clash, ideas collide, answers remain out of reach. Black holes are the meeting point of two great forces, the smooth, curved geometry of space-time and the jittery, unpredictable chaos of quantum fields. To understand one entirely, we must understand the other, and yet, merging them into a single unified theory has eluded physicists for decades. Black holes hold the key. Inside a black hole, space-time curves so violently that quantum effects can no longer be ignored. But quantum mechanics becomes so extreme that classical space and time cease to have meaning. Deep inside the event horizon lies the one place in the universe where the two greatest theories humans have ever created must both be correct. And yet neither fully works. It is here, in the darkness of a black hole, that we may find the foundation of a future theory, a quantum theory of gravity. And when that day comes, the universe may reveal secrets we cannot yet imagine. But even without that final theory, black holes already reshape our understanding of space. They show us that the universe does not simply exist in 3 dimensions, but may store information on surfaces, on horizons, in ways we never predicted. The holographic principle, one of the boldest ideas in modern physics, suggests that the universe itself may function like a projection, where everything we see in 3 dimensions is encoded on a distant boundary. And where does this idea begin? With black holes. Black holes are not merely cosmic objects. They are laboratories, places where the universe conducts experiments at extremes beyond any machine we could ever build. They press matter into forms beyond imagination. They twist space-time until the familiar bends into the alien. They transform energy, information, and geometry into a dance that defies intuition. And perhaps most profoundly of all, they remind us how much we do not know. We do not know what happens at the singularity. We do not know whether information survives. We do not know whether wormholes exist. We do not know how many black holes roam the universe unseen. We do not know what role they played in the dawn of time, or what role they will play at the end of everything. We only know this: black holes are more than dark pits. They are cosmic challenges, and humanity has never turned away from a challenge. Already we build telescopes capable of imaging the unseeable. Already we send gravitational wave detectors to listen for distant collisions. Already we explore the mathematics of the impossible. Already we dream of probing the event horizon itself. One day we may send a probe closer than ever before, skimming the edge of the event horizon to gather data no human has ever possessed. Machines may drift where no spacecraft has ever dared. Robots may dive into the jaws of a black hole, transmitting data until the horizon swallows their final signal. Humanity may one day witness, with eyes and instruments, the moment we cross into the unknown. And if our species endures long enough, we might even control black holes, harness their energy, orbit them, build colonies around them, powered by their radiation, use their gravity to bend space-time, perhaps even to travel unimaginable distances. Black holes are not only the end of stars, they may be the beginning of civilizations yet to come. For now, we study them from afar. We observe their shadows. We listen to their collisions. We calculate their orbits. We imagine their depths. But the journey is only beginning. Because in the end, black holes remind us of something profound. The universe is vast beyond comprehension, mysterious beyond understanding, and beautiful beyond imagination. And though black holes conceal their secrets behind horizons we cannot cross, they illuminate the greatest truth of all. That mystery is the engine of discovery, and the unknown is the greatest adventure of the human mind. And yet, even after everything we've uncovered, the black hole remains a puzzle with pieces missing, pieces scattered across the universe, waiting for us to find them. Because the deeper we look, the more the universe seems to whisper a startling truth. Black holes may not be isolated monsters lurking in the dark. They may be part of a larger cosmic pattern, a structure woven into space-time itself. Some theories suggest that every black hole has a unique fingerprint, a pattern hidden in its mass, its spin, its charge, and perhaps something more. Something encoded in subtle ripples of space-time that we have not yet learned to read. If we could decipher this code, if we could interpret the information hidden within a black hole's gravitational waves, we might unlock secrets about the early universe, about dark matter, about the very origin of space and time. Imagine a universe where black holes are more than collapsed stars. Imagine they are relics, ancient fossils left behind from the moment of creation. Primordial black holes born not from stars but from the chaotic energy of the Big Bang itself. If they exist, they could be tiny, smaller than atoms, yet with masses greater than mountains. They could be everywhere, passing through planets, drifting through galaxies, leaving no trace other than the quiet tug of their gravity. And if they are real, they could explain one of the greatest mysteries of all: dark matter. Dark matter, an invisible substance that outweighs all visible matter in the universe, might not be exotic particles. It might be a vast population of tiny, ancient black holes, quietly sculpting the structure of galaxies without ever revealing themselves through light. But the rabbit hole goes deeper. Some scientists wonder whether black holes might be responsible for another cosmic mystery: gamma-ray bursts. These incredibly powerful explosions, lasting mere seconds, release more energy than the sun will emit in its entire lifetime. They come from the collapse of massive stars, the collision of neutron stars, and perhaps, in rare cases, the birth of new black holes. A gamma-ray burst could sterilize an entire region of the galaxy. It could burn atmospheres, boil oceans, halt evolution on countless worlds. And yet, without black holes forming through such cataclysms, the heavy elements needed for planets and life might never be created. Creation and destruction intertwined. Darkness and light forever entangled. Black holes balancing the cosmic equation. But even as we uncover these connections, another strange possibility emerges. What if black holes are not the ends of stars, but the seeds of new universes? Some cosmologists propose that every black hole's singularity might be a bridge, a point where space-time does not collapse into nothingness, but rebounds into a new expanding cosmos. A baby universe, connected to ours through a one-way passage hidden behind the event horizon. What if our universe was born from such a black hole? What if the Big Bang was not a beginning, but a transition? If this idea is true, then black holes are not cosmic dead ends. They are cosmic wombs, gateways, portals to new realms, invisible to us yet fundamentally connected to everything we know. Our universe could be part of an endless lineage, with each black hole spawning another universe, each new cosmos branching out like a tree of infinite possibilities. And if that is true, then somewhere, inside the heart of a black hole, another universe may be expanding, its own stars forming, its own galaxies emerging, its own mysteries waiting to be discovered. Perhaps civilizations in those universes look up at their own stars and wonder about their origins, unaware that the answers lie beyond the horizons of their own black holes. And perhaps their questions echo our own. But even if we leave speculation and remain firmly in the known, black holes still reshape our view of reality. Consider the spin of a black hole, how it drags space-time around with it, twisting it like a cosmic whirlpool. This process, called frame dragging, blurs our understanding of direction and motion. Inside such a region, every path forward might loop back on itself. Time might flow in circles. Causality might become tangled. And for the fastest spinning black holes, something extraordinary may happen. According to theory, if a black hole spins rapidly enough, its event horizon tightens, and inside it lies a region where the usual rules cease to apply. In this zone, space can rotate faster than light. Not matter, space itself. And in such a place, strange paths through space-time may exist. Paths that lead back to your own past or sideways into parallel realities. Physics warns us these paths might be unstable, collapsing under the slightest disturbance. But the mathematics allows them, at least for a moment. Black holes carry within them the potential for time travel, mathematically possible, physically elusive, eternally mysterious. And the more we learn, the more black holes reveal their influence on cosmic evolution. They shape galaxies, govern star formation, regulate matter, and guide the flow of cosmic energy. Without them, galaxies might be chaotic swarms without structure. Stars would form differently. Planetary systems might not stabilize. Life, as we know it, might never rise. Everything we are, everything we see, is influenced by something we cannot see. But perhaps the most astonishing realization of all is this. Despite their enormous power, black holes are astonishingly simple. With only a few properties, mass, spin, and charge, they become almost featureless. Two black holes with identical properties are indistinguishable no matter what formed them, no matter what fell into them, no matter what they consumed. This simplicity, known as the no-hair theorem, tells us that black holes forget their pasts. A black hole that once devoured a star or a planet or even an entire civilization bears no mark of its feast. It is memoryless, indifferent, eternal. And yet, The paradox returns. If black holes forget, where does information go? Does the universe keep secrets, or does it merely hide them? The more we learn, the more contradictions emerge. The universe feels like a book written in two languages, relativity and quantum mechanics, each elegant, each powerful, and each incomplete without the other. And somewhere, hidden within a black hole, the final translation may lie. Perhaps one day, far into the future, we will understand the true nature of black holes. Our technology will improve. Our theories will converge. Our curiosity will persist. And humanity will finally reach a place where the mysteries once hidden behind the event horizon become clear. Until then, the black hole remains the ultimate symbol of the unknown, a silent guardian of cosmic secrets, a boundary between what is understood and what lies beyond comprehension, a reminder that the universe is not only stranger than we imagine, but stranger than we can imagine. And so, standing at the edge of all we know and all we hope to understand, the black hole looms before us, not simply as a region of darkness, but as a profound symbol of the universe's deepest, most intricate mysteries. And yet, the more we contemplate it, the more we realize that the black hole is not just a question mark at the end of cosmic sentences, but a gateway to new ideas, new philosophies, new ways of imagining reality. Because beyond the math, beyond the physics, beyond the complexities of relativity and quantum theory, black holes force us to confront the very nature of existence itself. The universe is vast, perhaps infinitely so. And within that immensity, black holes are like punctuation marks, places where the flow of space-time itself shifts, where the story momentarily pauses, or crashes, or loops back on itself. And the more we learn about them, the more they appear not as aberrations, not as flaws in the structure of reality, but as essential components of its architecture. They shape galaxies, they influence star birth, they sculpt the cosmic web. They challenge our understanding of time and space. They whisper secrets about the beginning and end of everything. But perhaps the most astonishing part of all is how black holes change us, our imagination, our curiosity, our hunger to understand. They push human thought to its limits. They stretch our intellect. They invite us to grapple with the unimaginable. And so, to continue our journey into this deepening mystery, let us step back, far back, beyond the stars, beyond the galaxies, beyond the veil of the observable universe, to explore a concept that extends the influence of black holes far beyond their immediate surroundings. Because black holes may not simply exist in space, they may play a role in creating space. Some scientists believe that the fabric of space-time may be composed, in part, of tiny quantum bits, interwoven threads of information. And astonishingly, the mathematics of how these bits connect resembles the mathematics of entanglement, the quantum phenomenon in which particles separated by vast distances remain mysteriously linked. Black holes appear to be woven from these same threads. The event horizon itself may operate as a kind of storage surface, a cosmic ledger, recording the information of everything that falls in. And if this is true, then the universe itself may behave like a hologram, where all the richness of three-dimensional space emerges from information encoded on two-dimensional surfaces. This is not poetic metaphor. This is frontier physics. Black holes are teaching us that space is not a smooth stage on which matter acts. Space is dynamic, emergent, possibly woven from quantum information itself. And in the depths of a black hole, that information becomes compressed, tangled, twisted into patterns we have yet to decode. If we could decipher how information behaves at the event horizon, we might reconstruct the foundations of space-time, perhaps even uncover the equation that unites gravity and quantum mechanics, a unified theory sought for over a century. Imagine that. A tiny black hole, smaller than an atom, holding the blueprint of the universe. Such a concept is not fantasy. It emerges from the mathematics of string theory, of loop quantum gravity, of holography, of entanglement entropy. It emerges from ideas so bold they once seemed impossible, but now stand at the edge of becoming testable. Black holes are not merely cosmic monsters, they are cosmic instructions. And in studying them, we begin to understand that the universe is not a static place. It grows, it evolves, it organizes itself in ways no one could have predicted. And black holes, far from being exceptions, appear to be essential components of that organization. Let us imagine for a moment the early universe. A chaotic soup of energy and matter, expanding rapidly, cooling gradually, forming the first atoms, the first stars, the first galaxies. And scattered throughout this primordial landscape were the seeds of black holes, some born from dying stars, others formed directly from fluctuations in space-time itself. These early black holes may have acted as anchor points, gathering matter, pulling it into spirals, helping galaxies form around them. Without them, galaxies might never have taken shape. Stars might have formed without order. Planetary systems might have been rare. Life, as we know it, might never have emerged. It is a strange irony. The most destructive objects in the universe may have been necessary for the creation of worlds like ours. But even deeper questions arise as we study black holes more closely. Consider the rotation of a black hole. When a star collapses, any tiny rotation becomes amplified by the conservation of angular momentum into an extraordinary cosmic spin. Some black holes rotate at such extreme speeds that the space around them becomes twisted into a spiraling vortex, dragging time itself into rotation. Inside this region, known as the ergosphere, strange phenomena become possible. Particles can escape with more energy than they entered. Energy can be extracted from the black hole's rotation itself. This idea, proposed by physicist Roger Penrose, hints at the possibility that future civilizations might harness black holes as enormous power sources, engines capable of producing energy far more efficiently than any star. Just imagine, alien civilizations dwelling near black holes, building structures that orbit close to the event horizon to capture unimaginable energy. They might use black holes the way we use fossil fuels or nuclear reactors, vast generators of cosmic-scale power. And why not? Around a rotating black hole, energy is everywhere, free for the taking to those who dare approach. But approaching a black hole is no simple matter. The gravity grows stronger, time slows, light bends, tides stretch, the horizon approaches, and once crossed, there is no escape, unless the horizon is not absolute. This idea, controversial and remarkable, proposes that quantum effects may allow tiny bits of information, or energy, to escape the horizon. Hawking radiation, the theoretical emission from black holes, suggests that black holes are not perfectly dark. They glow faintly, slowly losing mass, slowly evaporating. This radiation is unimaginably weak for large black holes, but the concept is groundbreaking. It means that black holes are not eternal prisons. They leak, they change, they evolve. And somewhere in that slow leak lies the answer to the information paradox, the question of whether black holes destroy information or preserve it in some hidden form. If information escapes in scrambled form through Hawking radiation, then black holes may be cosmic mixers, destroying the original structure of information but preserving its total quantity. But if information is stored on the event horizon itself, it may be encoded holographically, waiting to be released when the black hole evaporates. And if neither explanation is correct, then the universe holds a deeper secret still. Perhaps information escapes through wormholes. Perhaps the singularity bounces into another universe. Perhaps the universe does not treat information the way we believe. Perhaps reality itself is more flexible than our equations allow. But theory aside, black holes are real, and their influence extends across billions of light years. Consider supermassive black holes at the centers of galaxies, the engines of quasars, the hearts of active galactic nuclei. Some of these cosmic powerhouses emit jets of energy so immense they heat surrounding gas, preventing star formation on cosmic scales. These jets shape entire galaxies. They regulate cosmic evolution. They create order from chaos. Without them, galaxies might grow too quickly, or collapse inward, or never stabilize at all. Black holes are cosmic thermostats, balancing the temperature of intergalactic gas and ensuring galaxies evolve in a stable, predictable way. In a sense, they act like gardeners, pruning the galaxies around them, influencing the growth of stars the way climate influences the growth of forests. They are not simply destroyers, they are caretakers. But while we observe their influence from afar, black holes remain shrouded in deep, tantalizing mystery. And nowhere is the mystery greater than at the singularity, the point at the center where our physics breaks down. At the singularity, density becomes infinite, curvature becomes infinite, and space-time collapses into a place with no volume, no dimensions, no meaning. This is what Einstein's equations predict, but nature rarely allows infinities. Infinities are clues that our theories are incomplete. This is why physicists believe the singularity is not truly a point, but a region governed by quantum gravity, a yet undiscovered theory that merges the large-scale geometry of space-time with the small-scale uncertainty of quantum fields. Some propose that the singularity is replaced by a quantum core, a region where space-time becomes discrete, granular, woven from tiny loops or strings or quantum bits. In this view, the collapse stops before reaching infinite density. Others suggest that space-time itself might tunnel into a new configuration, forming a bounce, a moment where the collapse reverses, expanding into a new universe. If so, every black hole might contain a universe. And every universe might be inside a black hole, a cosmic nesting doll of realities within realities. This idea, while speculative, offers a stunning vision. Black holes as the seeds of existence, not merely the endpoints. But to understand black holes fully, we must look not only at what falls in, but at what happens around them. Space warps in predictable ways, described by Einstein's general theory of relativity. Light bends, time slows, orbits precess, gravity waves ripple. And yet, even in these familiar behaviors, black holes create extreme versions of physical phenomena that would be impossible anywhere else. Imagine standing, hypothetically, on a safe platform near the event horizon of a black hole. Around you, the universe would appear distorted. Light from stars behind the black hole would bend around it, creating rings, Einstein rings, patterns of warped light. The black hole would glow at its edges, not from its own light, but from the swirling matter in the accretion disk. Time would pass differently for you than for anyone farther away. A minute near the horizon might equal hours, days, or years elsewhere. Live too close, and you could return to a universe that has aged centuries while you experienced only moments. A black hole is not just a place. It is a time machine, altering the flow of time in ways no human has experienced firsthand. But to truly grasp the black hole, we must consider its birth. When a massive star collapses, its outer layers explode in a supernova, while the core contracts inward. The pressure becomes so immense that electrons and protons fuse into neutrons, creating a neutron star. But if the mass is too great, even this incredibly dense state cannot withstand gravity. And so the core collapses further. The neutrons are crushed. Matter collapses beyond the limits we can comprehend. And the black hole forms. This transition from star to black hole is among the most violent events in the universe. The supernova blast releases more energy in seconds than the sun will emit in its entire lifetime. And yet within that chaos, a new cosmic object is born, a black hole with gravity so intense that it reshapes the universe around it. If the black hole is spinning, it may produce jets, beams of energy blasting from its poles. These jets can stretch thousands or even millions of light-years into space. They can ignite gas clouds, trigger star formation, or carve entire regions of space clean. Black holes sculpt the cosmos with invisible hands, and this cosmic influence extends far beyond the galactic scale. Consider binary black holes, pairs of black holes orbiting each other. As they spiral inward, they emit gravitational waves, ripples in space-time that travel across the universe. These waves, first detected by LIGO in 2015, confirm a prediction Einstein made a century earlier. We are now listening to the universe through a new channel. Not light, not radiation, but gravity itself. Gravitational waves reveal events that no telescope can see. They carry information from black hole mergers, from neutron-star collisions, from cosmic events hidden behind dust and gas. And what we learn from these waves is astonishing. Some merging black holes are unexpectedly massive, 30, 40, 50, even 80 times the mass of the Sun. Their existence challenges our understanding of stellar evolution. Others show unusual spins, suggesting complex evolutionary histories. Some mergers occur in regions where stars should be scarce, hinting that black holes may form and merge in places we never expected, like the centers of globular clusters or dense star-forming regions. Each detection expands our understanding of black holes. Each detection brings new questions. Each detection deepens the mystery. But the greatest mystery remains the singularity, where time, space, matter, and energy converge into something beyond imagination. What lies at the center of a black hole? A point? A ring? A bridge to another universe? A quantum core? A region where time ceases? A region where time begins? We do not know, not yet. But black holes are guiding us toward the answer. For now, we are left with a cosmic paradox. Black holes are simultaneously the simplest and most complex objects in existence. They can be described by just a few numbers: mass, spin, and charge. Yet the physics inside them may represent the deepest mysteries of the universe. Black holes are cosmic mirrors, reflecting the limitations of our understanding. They force us to ask profound questions. What is space? What is time? What is reality? Is the universe finite or infinite? Why is there something rather than nothing? The journey continues, and with it, our imagination expands. Because black holes are not endpoints. They are invitations, gateways to deeper understanding, doors to realms of physics we have only begun to glimpse. And as we peer into the abyss does not simply stare back. It challenges, it provokes, it beckons.